Hello learners, welcome to this course on Fundamentals and Programming of 8085 Microprocessor. In this tutorial, I will be discussing about how to interface a ADC0808 IC, which is a 8-bit analog to digital converter with 8085 microprocessor. So first let us start with the fundamentals of analog to digital converter 0808 IC. So ADC0808 IC is a monolithic CMOS device with a 8-bit analog to digital converter. So an analog signal can be converted into a digital data. This is required because our microprocessor or a microcontroller is a digital device. It accepts only digital data. So we need to convert an analog signal from a sensor. So most of the sensors are analog in nature, which means it will produce an output in terms of voltage or current with respect to any physical quantity. For example, if I take a temperature sensor, so a temperature sensor will produce a analog value, voltage or current, in relation to the temperature. Same way we have pressure sensors, flow sensors, etc. So this data, analog signal, needs to be converted into digital, then only it can be processed by a CPU. So here we have a 8-bit analog to digital converter, which means the result of the A to D will be a 8-bit result. So after the conversion process, the A to D converter will give a 8-bit result. And this IC, it also supports a 8-channel input. So 8 sensors I can connect to the IC. So thereby a particular input can be selected for the conversion purpose. So that is done with the help of a multiplexer. So 8:1 multiplexer. So this 8:1 multiplexer will select a particular channel and route it to the analog to digital converter. So we have only one analog to digital converter, but it can support up to 8 inputs. So the selection of the input is done by this multiplexer, 8:1 multiplexer. And this A to D converter is of successive approximation type. So I will discuss about this in detail. And the main advantages of this ADC 0808 or 0809 are in terms of high speed operation, high accuracy in representing a digital data in relation to the analog signal, minimal temperature dependence, excellent long-term accuracy, repeatability in the results, and it consumes very minimal power. And a main advantage of this chip is it does not require any external zero or full scale adjustment. So only 5 volt DC will be sufficient. So here I show the architecture of your A to D converter. So the important part of this A to D converter is this SAR block. This is a successive approximation register, so which holds the binary values. As I said, this ADC is going to produce a 8-bit result. So here this register is also going to be of 8-bit data. So this register, it can vary from 8 zeros and it can go up to 8 ones. So depending upon this successive approximation register content, an analog signal will be generated by this register ladder. So here I show a register ladder, which is nothing but a R2R ladder type, which is a DAC, digital to analog converter. So depending upon the binary value given here, a corresponding analog voltage will be generated. So this is the opposite of your ADC. This is DAC. So I give a digital data and it produces an analog voltage corresponding to that digital bits. So depending upon the successive approximation register content, the corresponding voltage will be generated by this R2R ladder and it is given as one of the input to the comparator. And we have connected the sensors we can connect up to 8 sensors IN0 to IN7 to this 8-channel multiplexer. So this 8-channel multiplexer selects a particular input and gives that voltage to the comparator. So now this voltage, input voltage, is compared with the R2R ladder type generated voltage. If it matches, if the input from the sensor matches with this DAC output, register R2R ladder type output, then that is the corresponding bit pattern for the input voltage. Then that bit pattern can come as an output from this ADC IC. In order to select the input channel, an address latch and decoder block will make use of the select lines A, B, C to select a particular channel. So for example, here I have shown A, B, C. So if all the three are low, which means 0, then IN0 will be selected. Low, low, high, IN1 will be selected. Low, high, low, IN2 will be selected. So like that it goes on. So if I put high, 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 then IN7 will be selected. So a particular input can be selected and that voltage can go to the comparator input. And this voltage is compared with the R2R ladder type voltage generated, and if it matches, if the input voltage and the voltage generated by the R2R ladder type matches, then the corresponding bit is the digital pattern for that analog voltage. Then that bit pattern, it comes as an output through this output latch. So the output will be enabled only when I have this output enable pin to be high. If output enable pin is high, then the output will come in the pins of the ADC. So in order for this R2R ladder type to work, we need to supply a reference voltage. So we provide a reference voltage here. So up to 5 volt reference voltage we can provide. So if I provide a 5 volt reference voltage, then the input voltage can swing between 0 to 5 volt. It can be any value between 0 to 5 volt. Then this ALE is used for representing the address through the select lines. Then we also have a control and timing circuit which provides the start of conversion process provided by the user. Same way clock is provided by the user. So clock determines the speed of conversion. So up to 500 kilohertz clock we can able to connect to the ADC IC, and the end of conversion is indicated by the ADC IC. So the CPU, what it can do, it can assert this SOC, start the conversion process, then the conversion will start. Once the result is available, once the 8-bit data is available after the conversion process, then the ADC sends a signal through this end of conversion process. So this signal will be received by the CPU. Upon receiving this signal, the CPU can read the 8-bit data from the ADC. So if I want to see the resolution of this ADC, so resolution is given by the reference voltage divided by 2 power n minus 1, where n represents the number of bit of a to D converter. So here this is a 8-bit A to D converter. If I take a reference voltage of 5 volt, I have represented it as 5000 millivolt, 2 power 8 minus 1, which means it is 256 minus 1, which is 255. So what we do is 5000 millivolt divided by 255, it comes about to be 19.6 millivolt. So this is the minimum voltage which can be resolved by your A to D converter. So if the voltage is 0, if the input voltage is 0, then I will get a binary bit pattern of 8 zeros. The next voltage which can be resolved is 19.6 millivolt. So the 19.6 millivolt will give a binary bit pattern of 7 zeros 1. Then next one will be 38, approximately 38 millivolt. So in that case, I will get 1 0 as an output. So this is the minimum resolvable voltage of your ADC. If I want to increase the resolution, what I can do? I can change the reference voltage. By changing the reference voltage, instead of having 5000 millivolt, I can have it to be 2.5 volt. In that case, 2500 millivolt. Then my resolution will be off. It will be something about 9.3 or 9.8 millivolt. 9.8 millivolt will be the resolution at the time. So we can resolve much more smaller voltages by changing the reference voltage. Now let us look at the pin details of this A to D converter. So this is a 28 pin IC. So here you can find pin number 26, 27, 28 is nothing but IN0, IN1, IN2, and 1, 2, 3, 4, 5 is IN3 to IN7. So these are the 8 inputs. So I can connect 8 sensor inputs to these pins. Then there is a start the conversion process which is given by the CPU, and end of conversion process indicates the conversion has been completed. Then there is an output enable pin to get the output from the output latch to the digital pins of the ADC converter. Output enable pin, again it will be provided by the CPU. Clock signal, we can use a crystal, or we can use some crystal oscillators or some oscillators to generate the clock frequency for this ADC. Then there is a power supply line. Then there is a pin to give the reference voltage, ground line. This 2 power minus 1 to 2 power minus 7 represents the binary output coming out of your ADC converter. Then there is a V reference minus voltage, ALE address latch enable. Then the select lines for the multiplexer to select a particular input. I have A, B, C. So this gives the pin details of your A to D converter. So now let us see how to interface this ADC0808 with 8085 microprocessor. So here we have a 8085 microprocessor. It is connected with the 8255, which is a programmable peripheral device. So please look at my earlier tutorial on programmable peripheral device to have a better understanding. So here it has 3 major ports, port A, port B, and port C. So port A is an 8-bit port, port B is an 8-bit port, port C is also an 8-bit port, but it can be divided into port C upper and port C lower. So port C upper is 3 bits, PC0 to PC3. Port C upper is again 4 bits, which is PC4 to PC7. So we are going to make use of port A to get the digital data from the ADC IC, and also the end of conversion signal will be obtained through this port C upper PC7 pin, and port C lower is used for sending the information to the ADC IC, like control lines or address lines for selecting a particular input, and also ALE and start the conversion process. So this is a ADC0808 IC. So here we can see the reference voltage is provided with 5 volt, and also the IC supply voltage is 5 volt, and output is also enabled with 5 volt. We can give a clock source 7490 IC, so up to 500 kilohertz clock can be generated, and it can be provided as an input to this ADC0808 IC. So an IN0, a sensor input is provided to this ADC. So after conversion process, the digital data will be available here, that will be read through the port A. From port A, it goes to the CPU. In order for this data to be read, first what it will do, the CPU will send the data through this port C lower. So the address lines PC0, PC1, PC2 should be 000, so that IN0 will be selected, and also it will enable this start the conversion process. After completion of the conversion, end of conversion will be indicated, and it will be read by the CPU through port C upper. So upon receiving this signal, the CPU will try to read the port A data, which is the converted result. So let us try to see the control register input output modes. So control register of this 8255 is an 8-bit register. So here the D7 bit represents an IO mode. So 2 modes are possible in 8255, which is BSR mode, bit set or reset mode, or IO mode. So bit set or reset mode is applicable only for your port C. Now we are going to use this 8255 as a IO mode. So the D7 bit is set to 1. Then D6 and D5 is used for mode selection of port A. So port A can be in 3 modes: mode 0, mode 1, mode 2. So mode 0 is a simple IO mode. Mode 1 is with handshake signals. Mode 2 is a bidirectional mode. So here for our program, we are going to use the port A in a simple IO mode. So that is 0, 0. We try to use it here. And what is the function for port A? We are going to use it as an input, because the digital data from the ADC0808 will come as an input to the 8255. So we are going to provide it with 1 here in D4 bit. Then port C upper also we are going to use it as an input pin, because end of conversion process will be generated by the ADC and will be given as an input to the port C upper. So IO function of port C upper also set to an input mode. Then mode B, port B, we are not going to use it. So we are not going to use this D2 and D1 bit. So D0 bit, we need to set it, port C lower. So port C lower is the output signals. Okay, so it will be set with 0. So the corresponding address for port A, port B, port C and control word register is given here. So 00 for port A, 01 for port B, 02 for port C and 03 for control word register of 8255. Now let us see a program on how to read a digital data from ADC0808 IC. So here a program to generate a digital signal from analog data. So we are going to use IN0 as an input pin. So the pin selection value will be 00. So the address lines A, B, C will be set to 00 so that IN0 will be selected. So first let us start with MVI, move immediate data 98 to accumulator. So what is 98? 1 0 0 1 1 0 0. So this one represents it's an IO mode. And next 2 bits is for port A. So port A 00 means it is in mode 0, simple IO mode. Then the next bit 1 represents port A, we are going to use it as an input port. Then port C upper also we are going to use it as an input port, because we have here PC7 coming as an input. Then port B we are not going to use it, so these 2 bits we can set it to 0 or 1, there is no issue in it. Then finally port C upper, port C lower, we are going to set it as an output port by putting it as 0. So this is 98. So 98 goes to your accumulator. From accumulator we are going to send the data to 03. 03 is a control word register. We are configuring the programmable peripheral device 8255. Next XR A. So we are going to do a XR operation of A with A. So if I have same inputs, then the XR output will be 0. So what we essentially do is we are clearing the accumulator. So after clearing the accumulator, we send that value to 02. 02 is your port C. So port C in the sense here. We are sending the value 0 to this port C, which means A, B, C will be set with 0. Thereby IN0 will be selected. And we have also sent 0 to this start the conversion process and ALE. So we have not yet initialized. We are just selecting the input here. Next, we are going to send 8 to accumulator. 8 in the sense 1 7 zeros. Sorry. 4 zeros and then 1 000. So which means the C3 bit we are setting it to 1, which means we are saying start the conversion process. So after selecting a particular input, we are saying start the conversion process. Then the ADC will start the conversion process. It will perform the conversion. So that is what we do here. So ALE and SOC is set to 1. then we try to make it to 0. So it's just a simple high to low pulse. So thereby conversion will start. So now we are going to read 02. 02 is port C. So port C we are going to read. Why? Because we need to check the end of conversion signal. So once the process is complete, end of conversion signal will be generated. Then that information can be used for reading the digital data. So we need to check this P7 bit. So in order to check that, we read the data in port C, then move the data towards left through carry. So rotate accumulator content left through carry, so that the PC7 data can come to the carry flag. Then I can check the carry flag whether it is set or not. If end of conversion is generated, then after executing this RAL instruction, the data will be available in the carry flag. Then the carry will be set. Upon carry is being set, I can read the data. So I'm going to continue this until I get a carry. So jump on no carry, read. So if there is no carry, again and again I am trying to read the port C data. Once the carry is generated, once the end of conversion is generated, it will come out of this loop. Then what we do? We read the port A. Port A is at 00. So we read port A and it gets copied into accumulator, and then that accumulator content is sent to the memory location. So thereby analog data, it's converted into a digital data, and that digital data is read by the 8085 microprocessor and it is sent to the memory location. So this is how an ADC0808 IC, analog to digital converter, can be used for reading the data from a sensor. Thanks for watching. Please subscribe for more technical learning. Thank you.